So we'll get started. Thank you too for attending. This is the final Compass lecture of the semester, and I want to introduce today's speaker, Claire Gasquet. She's a fifth year and hopefully final year grad student in the physics department. She got her start in research as an undergraduate at Dartmouth College, where she studied Earth radiation belts and fell in love with space sciences. She currently works at Berkeley's Space Sciences Laboratory, where she analyzes data from large NASA missions, including Parker's Solar Probe and the Ionospheric Connection Explorer. So let's welcome our speaker, Claire.
Thank you. All right. Well, first of all, thank you all for being here. It is the end of the semester. There's a million things going on at the same time. So thank you for taking the time to do this. All right. So we are here today, as you can see, to talk about the Northern Lights. Or are we? Okay, so let's start with, has anyone here seen the Northern Lights before? And if you're online, you can raise your hand, I can see you, or if you're in the room. Yeah, what's your question? I do mean in person. Thank you for clarifying. Has anyone seen it in person? No. Well, so fun fact, I haven't either, which is kind of funny seeing as I am studying them. Hopefully, at some point, it's on my bucket list. But over the past year or so, my collaborators and I have been studying something that actually looks a lot like the aurora. But we found out that it is in fact an imposter. I'm going to tell you the story of how we unveiled that imposter, what that actually means, and what we still need to do to understand it better. But I'm probably getting a little bit ahead of myself, because in order to understand what isn't an aurora, first we need to know what an aurora is. So why don't we start there? So to do that, we need to start at the sun. Maybe it's going to change for me. Let's find out. There we go, the sun. Okay, so the sun. From down here, it doesn't look that interesting. It doesn't really do much unless there's an eclipse or something like the one a couple months ago. I don't know if you all caught that. That was pretty cool. But out in space, the sun is actually a lot more interesting. And so what's happening out there looks something like this. So because the sun is not just sitting out there in space, it's actually constantly blowing particles off itself, right? The sun is very hot, it's very dense, the surrounding space is not. So there's something called the solar wind, which is constantly blowing away from the sun at the Earth. This is made pretty much of electrons and protons. It's charged particles that are coming at the Earth. And they are going at about 300 miles per second. To put that in context, miles per second, right? That means that from here down to LA, it would take about 1 second to get there. Or if you were flying across the country to visit your family for Thanksgiving, like I did, it'd take about 10 seconds, which is a lot better than the hours that I spent on a plane. But luckily for us, the solar wind is not very dense. In fact, if you had, the standard water bottle of the solar wind, if I'm looking at the amount of water in here, it's about 10 million water molecules. If this was full of solar wind, there'd be about 2,000 in here. So it's not very dense at all. The other thing that is good for us is the fact that Earth has a magnetic field. And in this video, you can kind of see the contour of the magnetic field. It's deflecting the particles around the Earth. What discipline are you all in, by the way? Physics, astronomy, physics, data science. All right, cool. So we have a mix. I don't know about you all online. You can put it in the chat if you want. Or not, either way, it's fine. Anyway, so if you've studied any sort of electricity and magnetism, you know that particles in a magnetic field will get deflected. And so Earth's magnetic field serves to deflect these solar wind particles around the Earth. And you see there's actually this distance here, which is kind of the closest that the solar wind can get to the Earth. That's where it's called the bow shock, because again, the solar wind is moving supersonically. It's faster than the speed of sound, so it creates a shock there. But this distance is determined by kind of a balance of pressures. The solar wind has a dynamic pressure, it's pushing, and then the magnetic pressure of the Earth's magnetic field is pushing back. And so where those two pressures are equal is where you get this distance. And so this is kind of what it looks like in steady state. Oh, people put things in the chat. That's great. Let's see what they said. Physics and astrophysics and math. Awesome. So we have a good number of people that are familiar with some physics and some other disciplines too. So that's great. All right. So this is kind of what it looks like in steady state, but sometimes the sun is not so well behaved. And then you get something like this. So this is a coronagraph. So the sun is behind this part of it that's been blocked out, and you're just seeing the upper atmosphere of the sun here. And the thing that you'll notice immediately, right, is that we're looking at a video of an explosion on the surface of the sun. This is called a coronal mass ejection. This happens sometimes. And when this happens, right, instead of that solar wind that's already moving pretty quick, suddenly you have something that's denser and moving faster, which means the dynamic pressure, if it hits the Earth, is going to increase a lot. And what that's going to do is it's actually going to break some of Earth's magnetic field lines. And eventually that's going to create the aurora. And here's a little animation of how that's happening. So we have the sun. This is from 2006, which is why it looks kind of clunky. But we have the sun. There's a coronal mass ejection. It explodes. Then this hot, dense material is going to collide with the magnetic field. It's actually going to snap the magnetic field, cause it to wrap around the back. And then you get what's called reconnection. When those field lines are squished together, that accelerates particles that then stream along the field line and create the aurora. Yeah, question.
The snap is temporary.
It's temporary.
Okay.
Yeah, it's not forever.
Yeah.
But it's that transfer of energy that's accelerating particles that's happening right in here. And again, it's not this field line that's doing it. It's kind of compressing all of them. Then you get this reconnection in there. You get particles that are streaming down, and you get the aurora. But yeah, the magnetic field does go back to normal after. Did you have a question too? Mm-hmm. It's the actual magnetic field lines of the Earth. Basically, you're just messing with the magnetic topology of the Earth, and that's causing particle acceleration, is the way to think of it. It's a little hard to wrap your head around, I know. There's still ongoing research about that. I think the bigger ones are definitely going to cause larger magnetic perturbations, but magnetic reconnection is kind of happening all the time, more or less. But if you're online, you're free to ask questions as well. I'll keep an eye out. Okay. Okay, super. Okay. All right, so this is how you get the normal aurora. Here's a video of what the aurora looks like taken from the International Space Station, which is kind of fun. So basically, the aurora is made when particles are accelerated to very high speeds way out in space. It can be through that reconnection mechanism I was talking about. There's a couple other ways to accelerate particles. But the idea in general is that you have acceleration that's happening way out in space. This is thousands of miles away from the Earth. And then those particles are streaming down along the magnetic field. They're hitting Earth's upper atmosphere, and they're heating it up, essentially. For any quantum or chemistry people out there, right, they're knocking the atmosphere into higher excited states, and then when it falls down, it's releasing the light. So when it cools, it's releasing the light. The different colors correspond to different, basically it's the different composition of the atmosphere. The green is coming from atomic oxygen. Sometimes you'll get red, which is also from oxygen. You'll get some blue from nitrogen. We'll talk a little bit more about that later. But in general, that's the aurora. I think I have an actual definition up here. There's the Merriam-Webster definition. I prefer the plain language one, which is just bands of light in the sky near the northern or southern poles, typically. It's created when high energy particles accelerated in space are colliding with the atmosphere. As a bit of an aside, there is evidence for aurora on other planets, right? We have Saturn and Jupiter over here, where we have the aurora near the poles. This one's Uranus. Uranus is a little weird because the magnetic field actually looks pretty different than Earth's magnetic field. And so you can get aurora that's not actually in the polar regions, but is elsewhere. Any questions about aurora before we keep going? Yeah.
So they, because of the definition, they didn't make her was some kind of
Yeah, without an atmosphere, you're probably not going to get an aurora. You need something to excite to create the light. Yeah. Okay. So you can get aurora that look that are different colors, like I said, from the different atmospheric constituents and different energy levels of the particles. They can have different structures and shapes that have a lot to do with either plasma turbulence or different things going on way out in space. But actually, one of these is not an aurora. One of these is an imposter. So we're going to take a vote on which one you think is the imposter aurora. And if you read the description of this talk, you might have a good idea of which one it is, and that's okay. But why don't we take a vote? So who here thinks the imposter aurora is Aurora A? And online, if you raise your hand, I can see you too. Okay, nobody thinks it's A. How about B? Does anyone think B is the imposter? We have 2 in the room that think B is the imposter. Okay, how about C? Anyone thinks C is the imposter aurora? Okay. And D? We have 1 for D. The folks online didn't vote, but that's okay. Or at least I can't see if they voted. That's fine. Well, remarkably, you're all wrong. The imposter aurora is Aurora A. Dun, dun, dun. So that is actually not an aurora at all. So let's see. Oh, we have something in the chat. What's in the chat? Someone said A, but I already said A. I don't know. I feel like they cheated. No, it's fine. It's fine. They're the smart one here. It's okay. All right. So Aurora A, this is not a real aurora, or at least it doesn't fit that definition that we had of the aurora from before. So if we can't call it an aurora, what can we call it? Well, allow me to introduce you to Steve. It's not a joke, it's its actual name. Steve is the purple arc that you see up there, and the picket fence is often associated with it. That's what you see beneath it. And this is an imposter aurora. It happens at latitudes that are lower than the normal aurora. It's still pretty high latitude. So think instead of like northern Canada, we're thinking southern Canada. Although sometimes it can be lower than that. And this is what we've been studying over the past year. I know that you're curious about the name, so I will explain that. So Steve was actually discovered by citizen scientists. These are people that don't necessarily have a formal scientific background or don't do this as their day job. But in this case, at night, they go out and they take pictures of the aurora, which can be used for science. And so they found this, and they initially thought that it was a new type of aurora that we had ever seen before. They thought it might be made by protons instead of electrons or something else, but they thought it was a type of aurora. And at roughly the same time, well, I think it was a little after, but anyway, some of the people that discovered this had also recently seen a movie called Over the Hedge. I don't know if you all have seen this movie. If you're between the ages of 20 and 30, there's a chance that you've seen it. I saw it as a kid, anyway. But so this is a movie about a group of woodland creatures that are living, I promise this is relevant. They're living in a woodland forest. And one day they discover a hedge, and it's something brand new that they've never seen before, and they don't know what it is. So this crazy looking squirrel says, let's call it Steve, because we don't know what it is. Maybe you can see the connection, right? This aurora chaser, they saw this thing that they had no idea what it was. They'd never seen it before. So they said, let's call it Steve, right? And then in the scientific community, we were like, okay, well, that's a good name, but it's not really sciencey. So we're going to rename it. And so we're going to call it Strong Thermal Emission Velocity Enhancement, or Steve. So we did keep the name. But
They do that on purpose, and just try to find things like associated.
yeah, it's a backronym, as they say. You start with a name and then you decide what it stands for. Yeah. But yeah, so this is Steve. And this has actually only been in the scientific literature since 2018. So it's only about 5 years old. And we still actually don't have a good idea of what it is, although we've been getting closer. Here's some other, question. That
wasn't the same thing.
It's not the same thing, it's related, and that's actually what a lot of this talk is going to be about. I think if we have time, we'll probably have time. Bless you. Okay, so here are some other pictures of Steve. It can sometimes exist by itself, like you see in these pictures. Often it's accompanied by the picket fence. Sometimes you get mostly picket fence. This is normal aurora that's on the northern horizon there as well. And like I said, we still don't really know too much about what it is. What's happening in the chat? Okay, sign in the chat. All right. Okay. Right. So Steve, picket fence. And then the question becomes, okay, but this looks a lot like an aurora, right? It looks like lights in the sky. How do you know that it's not that? And that's what we've been working on. And to do that, we're going to talk very briefly about the electromagnetic spectrum. I think based on folks' background, they probably already know a lot of this. Is it going to change? It's not. Okay. But if you are a student of physics or have taken a physics class, then you probably know that light can be thought of as a wave. Quantum folks might differ with you a little bit, but let's just stick with the wave definition for now. This is just a fun graphic that's showing you kind of the scale of different electromagnetic waves, where radio waves are roughly the size of buildings, microwaves are somewhere between a human and a housefly. What we're focusing on here is the visible spectrum, which is about the size of a bacteria. The slightly longer wavelengths in the visible spectrum appear more red, slightly shorter appears more blue. And when we're studying the aurora, we can actually look and see which colors are being created using something called a spectrograph. And if we decompose that, we can figure out what is creating each of the colors and start to diagnose some of the mechanisms for how it's being made. So that's where we're going to start here. So this is what the spectrum of a normal aurora looks like. On the y-axis here is brightness. I figured that numbers didn't really matter for this kind of talk, so just brightness. On the x-axis here is color. It's a rainbow. It's great, right? So you can really tell. In the normal aurora, right, most of the light, the brightest thing is this green line, which is coming from atomic oxygen. That's why most aurora is going to appear green. You look confused, did you? Yeah.
Is there a reason why it's mostly from oxygen? Because like, is it like there's more oxygen in the upper atmosphere, or is it that it gets excited more easily or something?
So this is, first of all, this is atomic oxygen. This is not molecular oxygen. So this is not the oxygen we breathe. Up there is a lot more atomic oxygen than there is down here. We're talking about altitudes that are about 100 kilometers up, 60 miles or so. Up there, you're above what's called the turbopause. Turbopause is about 85 kilometers. I might be explaining more than you want me to here, but basically below that, everything's nice and well mixed. So you get that nice like 70% nitrogen, 30% oxygen that we have down here, molecular oxygen. Up there, things start to stratify by molecular weight. So you get a lot more oxygen, and then eventually you get a lot more just like hydrogen and helium the higher up you go. But so oxygen is much more present there. It also has a lower excitation threshold. So it takes less energy to get the green than it does to get, for example, the blue or this red nitrogen. Right, so primarily green. You have a little bit of this red, which is also from oxygen, just a different excitation level. You have some of this red, which is from nitrogen, and then you have some of this blue. This is actually from the ionization of nitrogen. And as we're talking about, each of these actually takes a different amount of energy to make. To use actual numbers, right, to get this green, it takes about 4 electron volts. So if you have an electron that has 4 electron volts of energy, it hits atomic oxygen, it has a chance of exciting this emission. If we're looking at this red from nitrogen, it's about 7. This blue from nitrogen actually takes about 18 electron volts, so it's the most energetic to make that. And when you're looking at normal aurora, you're pretty much going to see all of these features. In order for particles that are accelerated way out in space to get this far down in the atmosphere, they have to actually have a fair amount of energy. They need actually hundreds or thousands of eV to get down there, typically. Electron volts, yeah. Which means that you're pretty much going to get the whole spectrum. In particular, you're always going to get that blue from the ionization of nitrogen, as well as the green, etc. Red, this red actually, it depends on the altitude. At lower altitudes, you tend not to see this just because the chemistry is such that it gets quenched, which means that things kind of interrupt the light before it can come out. But in general, most aurora, or pretty much all normal aurora, this is what you're going to see. But then when we look at Steve, this is what you see. So Steve looks really weird when it comes to aurora. You do have some of those lines that we were looking at before. You have a little bit of this green from oxygen, you have some of this red from oxygen, but it's a question whether it's really there. It's actually within the error that it might not be there. There probably is some of this red. But the main thing that we notice in Steve is that at all colors, you have a little bit of light. You have what's called a continuum spectrum. So you don't have those lines anymore, but now you actually have light at all the colors, and that's where you're getting that kind of whitish mauve color from. And we still actually do not know what is creating the continuum. There's a couple theories out there about exotic chemistry, what might be going on, but we're still not sure. We might get some clues by looking at its friend, the picket fence, and that's what we've been doing in the last year or so. So here's what a picket fence spectrum looks like. So in a picket fence spectrum, it looks more similar to the normal aurora than Steve does for sure, right? You have this massive green from oxygen, that's the primary feature. You have kind of a hint of these nitrogen emissions here. You don't have any of that red from oxygen, but this is at a lower altitude, so we kind of expect that. The weird thing is that you don't have any of that blue from nitrogen at all. And this is weird because, like I said, if there's particles that are raining down from space, like in the normal aurora, you're going to get some of that blue. That's just how it would happen. And so what this is doing is it's actually constraining the energy of the particles that are creating this picket fence. They're probably not from way out in space, and they have to be somewhere between 7 electron volts to make this, but they can't exceed 18, so otherwise we'd start to get some blue. And so that is kind of giving us a clue as to what might be making this. And so we sat down with that. And here's just the summary. This was mostly for the folks the last time I gave this talk. But anyway, particles raining down from space create some blue light. No blue light, not created by particles raining down from space. Therefore, imposter aurora. Okay. So the question becomes, if it's not an aurora, what causes it? As I said, we need energetic particles with enough energy to make that green and the red, but not enough to make the blue. And the hypothesis that we had was, instead of raining down, yeah, okay. No, it's okay. Yes. This on the horizon is the normal aurora. And south of that, this is the picket fence, and there's not really a strong Steve in this case. But this is just looking at the picket fence here, yeah. Yeah, but this is the normal aurora. Often you'll see them at the same time. It's just that the picket fence and Steve are farther south than the normal aurora. Yeah. Okay. So the hypothesis is right that instead of having particles that are raining down to create this, which we can't have because then when we get some of that blue light, the other option is that the particles that are colliding with the neutrals are excited right where you see the light. So it's happening right in space, like basically right where you see those pickets, that's where the acceleration is happening, instead of it happening thousands of miles away. And we were thinking about what might be able to do that. And the idea is that it might be local electric fields, right where you see the light, that are parallel to Earth's magnetic field. These streaks in the picket fence are pretty much aligned with Earth's magnetic field. And so if you have an electric field there, that can impart some energy to the electrons, and then that could potentially cause them to collide with the neutrals and create the light. So we set out on some data analysis and modeling to show, or to question, whether this hypothesis could be the case. There's something in the chat. All right, so online, Claire is asking, do Steves and picket fences usually occur together, or is it weird to see a picket fence with not a prominent Steve? So they usually do occur together. Most instances that we see have either Steve by itself or Steve and the picket fence. Seeing the picket fence by itself is a little bit weird, but these are also pretty rare. They've only been observed really since 2018, and so the statistics of it is not quite clear yet. So still an open question, but you could go become an aurora chaser and help us find out. Okay. All right. So we have our hypothesis. We set out to test it. And to do that, we wanted to look at some examples. So this is what they call a keogram. You have time on the x-axis here. On the y-axis is elevation angle. So 0 degrees is the northern horizon if you're looking due north. And then the southern horizon is 180 degrees. So it's kind of looking along the sky and you're looking at where the light is coming from. And so we have this data. The color is how bright the green line is, the most prominent feature of the picket fence. And we have a couple picket fences that we picked out here to do this analysis with. And what we did is we wanted to see, okay, so we know we never get blue light. What is the ratio of green light to that nitrogen red light that we get? And then from there, we're going to use that to compare with some of the models that we created. So we pulled all of those examples. We found the green luminosity on this axis, the nitrogen red is on this axis. There's a decently linear relationship between that. And so the number that's important here is this 0.34. That's the ratio of the green or the red nitrogen luminosity to the green line luminosity. That's what we were trying to see, if it was possible to match that number with a model that's driven by those parallel electric fields. That was what we were setting out to do. So to do that, we modeled how the local electrons would react to parallel electric fields. This is what's called an electron energy distribution function. It's basically just like the probability that an electron will have a certain amount of energy. So the energy is here on the x-axis. This is more or less think of it as a probability on the y-axis. And these black lines are what's happening as we are increasing the parallel electric field. So if you have just a 20 millivolt per meter parallel electric field, then all of your electrons are pretty much going to be less than 2.5 eV, right? So you're not going to create any of this light. The blue here, the green and the red are giving you kind of the limits for the green line, that nitrogen red, and the blue line for like when you're going to start creating that light. And so that you can see that, so as we move from 20 millivolts per meter up to 60, suddenly we have this population that's extending where you're going to start to get some of this green light, a little bit of this red. You're still not going to get any blue. As you keep turning it up, right, the ratio between green and red is going to start changing, right, because you're in different parts of the space here. You're still not getting any blue at 115. Once you get up to 170 millivolts per meter, you're starting to stretch and you're going to start to get some of the blue. So that's starting to constrain what we're looking at. Any questions about this? Okay, makes sense. Great, cool. So right, take home thing is increasing electric field strengths results in more electrons with higher energies, and you're going to start to get different color ratios. This is what the space looks like. We did this as a function of altitude on the y-axis, and then that electric field strength on the x-axis. And this is just plotting the ratio between the red and the green. In this area, you have small electric fields, you're not getting any emissions. These large electric fields are not modeled because they are not physically realistic. But we found that this 0.34 that we were looking for actually falls reasonably well within the physically possible space, if you will. And in particular, so 110 kilometers is a typical height for the picket fence. And so we were able to say, based on this modeling, that if you have an electric field that's between 80 and 150 millivolts per meter, that's within kind of our error there, it is likely that you would get a spectrum that looks pretty much exactly like the picket fence. So our hypothesis might be correct. It's possible. Modeling, you can never say 100% that it's sure that's exactly what's happening, but this is a viable way to create the light that we're seeing in the picket fence, basically. So then the question is, what does it matter if we call it an aurora or not an aurora? Why does it matter that it's a different mechanism? It's kind of interesting. So scientists actually use the aurora often to trace what's happening millions of miles away in space. So they often say that the aurora is like a TV screen for what's happening out in the magnetosphere, so far away. But if this is the case, right, if some of that light is being produced right there in space, then that doesn't work anymore. And we have to reevaluate our models of where the light is coming from, how the energy is moving through the system, and update it based on what we're talking about here. And it's particularly important because once we started looking at the picket fence and deciding that, okay, this might be parallel electric fields, maybe this is not normal aurora, we started finding other imposters out there. This is something that appeared in a scientific paper only in 2021. This is the only paper about it so far, to my knowledge. It's another imposter aurora. These are called fragmented aurora-like emissions. They look a lot like the picket fence, but they're actually north of the normal aurora. And they have the same thing in their spectrum, where there's not very much blue, and you have that weird ratio of green to red. Another one that's actually even more common is called enhanced aurora. So when you look at the aurora normally, if it's made by particles falling down, you kind of expect the brightness to be a smooth function of altitude. And so what's weird about enhanced aurora is you actually have a sharp discontinuity in the brightness. So you have a layer in here that is much brighter with a sharp discontinuity than the rest of it. And the interesting thing is, if you look at the spectrum of this, it also has the same pattern, where there is less blue and then there is more green and red compared to it. And so the hypothesis is that this could also be created by those parallel electric fields. And this in particular would be a problem for people who are using the aurora to trace things in the magnetosphere, because this would not be created by particles in the magnetosphere, it'd be particles right there. And so our next step, I told you that the hypothesis is viable, but we need to actually go and prove it. And so recently we've submitted a proposal for a rocket mission, which is hopefully going to get funded by NASA. It's not currently funded, but maybe it would be. And the idea would be to start by looking at the enhanced aurora, that last imposter that I just mentioned. See if we can fly a rocket through it and actually measure those parallel electric fields for the very first time. We would also have a second rocket to go up and measure the precipitating particles to make sure that everything is consistent with what we think is going on. And then this would be a pathway mission to then study Steve and the picket fence more, try to understand more about where those are coming from. With Steve and picket fence in particular, there are still a lot of unanswered questions, like what causes the actual structure, the on-off part of the picket fence? How are Steve and the picket fence actually related to each other? What causes Steve's purplish white color? And actually a lot more unanswered questions than this too. But for now, thank you for your attention. If you're interested in the actual paper that this presentation is based on, you can get it there with the QR code. My email's there. And with that, I'm happy to take any questions. Yeah. No. Good question though. I did include more of the actual science plots in this one. And the other talk, it was just the rainbow on the x-axis plots. Yeah. Other questions? Yeah. Sure. So the question is to talk a little bit more about the rocket mission. I do want to emphasize that this is not yet funded, which means that it's not yet a real mission. It was just a thing that we proposed to do. The idea is that, like I said, we would send 2 rockets. One of them, the low flyer, would go through the enhanced aurora and try to measure those parallel electric fields for the first time to see if they're there and to see if they match the magnitude that we predicted from the modeling, right? That 80 to 150 millivolts per meter, that's kind of what we're looking for. And then the high one is just characterizing what are the conditions in the upper boundary of this system. Because the idea is that if we have a parallel electric field down low, it's probably being caused or it's related to something that's happening higher up. And so we're looking to trace sort of the physics along the field line to see what's going on. Do you have any specific questions about it that you're wondering? That's a good question. So the enhanced aurora and the aurora in general, this is happening about 100 kilometers up. Satellites actually, even in low Earth orbit, tend to be like 500 kilometers or so. If you put a satellite at 100 kilometers, it would very quickly burn up in the atmosphere. So this is actually where the atmosphere is too dense for satellites. It's also, sometimes NASA will also send up balloons to make measurements. If you're trying to get above the atmosphere, this is actually too high for balloons. So rockets are kind of the only way that you can measure this in situ. We have those measurements from the ground, from the spectrum, and you could theoretically get space-based measurements, but again, they'd be remote. So you could pretty much only get like the spectrum of light, for example. But if you want to measure electric fields, really the best way to do it is to actually fly through them. And so a rocket is the best bet, even though it's going to be hard to hit the target for sure. But good question.
So 2 questions from the chat,
Okay.
both from Gretchen. Are there any transient luminous events that might resemble either Steve or the defense? And the second question, is there anything we might be able to learn from TLEs that could help us figure out what's going on with the defense?
That's a good question. So transient luminous events, these are things like elves and sprites. I don't know if anyone else has heard of them. These happen a little bit lower in the atmosphere. They're typically associated with thunderstorms, that kind of thing. Like above a thunderstorm, you'll get some cool lights that are called like sprites and elves and things like that. The physics is actually pretty similar. The modeling that we did for looking at the electron distribution functions, we are actually borrowing tools from that TLE community to do it. So yes, there might be some relationships. I think that, so I'm not an expert in TLEs. I think that some of the stuff that you're looking at with TLEs has to do with like atmospheric breakdown, which is similar to lightning. And this is probably not that, but I'm open to talking more with people from that community to try to figure out some of the similarities. Hopefully that answered the question. You're welcome. Any other questions?
Is the finger speaker on slide?